All right, guys, I'm going to go ahead and get rolling so we have enough time to get through all the material in this section because I have a little bit to finish up from the last lecture. Some of the stuff at the very end of, I've got a few slides at the very end of this lecture which are more kind of fun things. So if we don't happen to have a lot of time to talk about them, then so be it. They're fun things for me to talk about, and I think they're interesting, but you guys can determine whether you think they're interesting or not. But they're kind of cool genetic things. Okay, so in the last lecture, we started talking about the Hardy-Weinberg equilibrium. We went through the basics of the math and plugged in some general numbers just to see kind of how it works. Okay, but ultimately, the real practical application, the real thing that you would need to be able to use this for, and ultimately the thing that you end up seeing in the board review books when they use this is, and this is typically how you would use this. You can use it certainly for other things, but this is typically what they'll use it for, is to determine the rate of carriers of an autosomal recessive disease when you know the incidence of the disease, right? Usually, we're able to ascertain the incidence of a disease, right? You know, hospitals keep records and you can calculate that. Well, you can actually use the Hardy-Weinberg equilibrium if you know the incidence of a disease to go back and figure out what is the rate of carriers of that disease in the population. And the other cool thing, if you consider it cool about this, is sometimes I think the numbers are a little shocking to people, how frequently you see the carriers in a population. So one example we're going to use in this, so what I'm going to do is I'm going to go through with you the pure math way of doing it, the hard way of doing this first, and then I'm going to show you there's a much easier way of doing it where you can just about do it all in your head, okay? And that's the way I do it in case you're wondering. But if you absolutely have to, you can use the long version if you want. Okay, so here we have an example of a disease, PKU. Okay, we've already talked a little bit about PKU. The incidence is about 1 in 10,000, okay? So we'll assign the disease-causing mutation, the designation Q, okay? Doesn't matter which way you do it, so it could be the reverse, you could assign it P, so it's P and Q. So the disease causing we'll say is Q, that means the normal gene is P. So QQ, those would be our affected individuals, right? They have 2 mutant copies, so that would be this 1 in 10,000. That Q shouldn't be right there, okay? Sorry about that. So it should be QQ equals 1 in 10,000, right? So we know the incidence of the disease, and the incidence of the disease is also the incidence of people who have 2 mutated copies. So it's 1 in 10,000. So we can actually, because QQ is Q squared, you can actually take the square root and figure out the incidence of Q. So the incidence of Q is 0.01, okay? Or we could actually say it's also 1 over 100. So the square root over 1 over 10,000, so the square root of 10,000 is 100. So you can also use this nomenclature if you'd like. And I think it's easier to use that, especially if you have one where it's an even square root, okay? And if I give you one on the exam, I'm going to give you one where you can do the square root pretty much in your head. Okay, so because we know the incidence of one gene, we can calculate the other gene, right? So the other gene is 0.99, so that's the gene frequency. So the gene frequency of Q is 0.01, and the gene frequency of P is 0.99, okay? So what I ultimately am asking you is, what's the incidence of carriers? So the incidence of carriers are the incidence of people who have 1 P and 1 Q. And how do you determine that from the Hardy-Weinberg equation? You take 2 times P times Q. Okay, and that's what I've actually done here. And when you do that math, you're going to come out with 0.02, which is also equivalent to 1 in 50. Okay, so the number of carriers for PKU is about 1 in 50. So that sometimes shocks people. It shocked me the first time I ever did any of this stuff. I was like, wow, you really see the carriers with very high incidence, even with something that's kind of on the borderline between common and rare, like PKU. 1 in 50. That means in all likelihood, several of us in this room have are carriers for PKU. And a lot of the other autosomal recessive diseases that we talk about. That's, at least to me, that was shocking. Okay, so I promised you that there's going to be an easier way to do this, okay? And why is there an easier way to do this? First of all, when we look at this math, look at this, 0.99. For all intents and purposes, 0.99 is 1, right? 1 times anything is itself. So you can actually take that out of the equation, right? So therefore, the equation just becomes 2 times Q. And I've got an example here where we've done this. So I can actually just do it with the last equation. So we had, and this is how quickly you will be able to do it. Okay, the incidence was 1 in 10,000. That means the square root of that was 1 over 100, and multiply it by 2. That's 2 over 100, or 1 in 50. Wow, I just took something that looked real complicated and made it much simpler, right? That's a much, much, much easier way of doing it. Now, if you don't have an even square root, it's a little bit harder because you're going to have to plug in a little bit of a different number, but you can still use a similar principle. But if I give you one, I'll give you an even square root, okay? But here's another one, and this is a real-world scenario, cystic fibrosis. Let's just go through it. The incidence happens to be about 1 in 2,500. Luckily for us, 2,500 is an even square root. So the square root of 1 over 2,500 is 1 over 50. And then I told you all you got to do is take that and multiply it by 2. 1 over 50 times 2 is 2 over 50, or you can reduce that to 1 over 25. So the incidence of carriers of CF and usually we're talking about a specific, in amongst Caucasians in this case, 1 in 25 whites is a carrier for cystic fibrosis. That's also should jump out to you as being something that's at a very high rate in a population. And we're going to touch on that a little bit later in this lecture. Okay? You see how I did that? Okay, so if the number, the incidence number doesn't happen to be an even square root, you can still apply the same thing. It'll still be 1 over whatever the square root is you get out of your calculator, and then just put 2 over whatever the square root you got out of your calculator is, and that'll give you the approximate incidence. Okay? Makes your life much, much, much simpler. But you can use the long version if you want as well. And once again, the reason that works is because one of the numbers is so close to 1 that we can basically kick it out of the equation. It doesn't significantly change the number. Okay, so now we're going to move on to the complications of pedigrees and also some things. We're also going to talk about some other genetic terms that influence genetic variation as well. So it's both complications and variation, because there are things that could complicate the pedigrees a little bit. So the first one I want to talk about is variable expression. You should be able to compare and contrast each of these when we're done. So variable expression is where you can have a particular genetic disease where the range of symptoms is a very broad spectrum. And NF type 1, this is one we've already talked about, neurofibromatosis type 1, is one where you have a very high range of possible symptomology. In some cases, even within the same family who have the same exact mutation type. A lot of different types of mutations could cause NF type 1, but even within the same families who inherit the same mutation type, you see this broad spectrum of symptoms. And you saw some of that in the earlier pictures. I gave you some extreme examples of the neurofibromas where they were just covered in neurofibromas. Whereas in some of the others where I was showing you the cafe au lait spots or the axillary freckling, you could see in those individuals they didn't have, in those cases I don't even think you could see any of the neurofibromas. They probably had some somewhere. but you get this big wide spectrum, okay? And that's variable expression. That can complicate a picture. So some genetic diseases show that. And what it indicates is there's other things going on that are affecting the expression. Could be environmental, could be other genes are affecting the expression ultimately. And I think there's some later lectures where Dr. Gardner is going to talk to you about some of that stuff. So that can certainly happen. The next term, pleiotropy. Pleiotropy is a disease where you have a single mutation. So right now we've really been talking about single diseases caused by single gene mutations. A single mutation causes symptoms in multiple different organs. Okay? And actually that's probably more common than uncommon. We have seen some diseases, for example, that just seem to affect red blood cells. But many genetic diseases affect multiple different tissues. Okay? Marfan syndrome, a good example of one we've already seen. Okay? In Marfan syndrome, you see symptoms in heart tissue. You see symptoms in the bones. You see symptoms in the eyes. These are seemingly unrelated tissues that are all showing symptoms due to one particular genetic defect, which was a defect in the, what gene? Fibrillin gene, right? Guess not everybody studied the PowerPoint yet, right? So that is something you need to know. Okay, the next is germline mosaicism. Okay. All genetic diseases, they start with a new mutation somewhere. Occasionally, what you can have is a new mutation that affects all or part of the germline, but it's not affecting enough of the somatic tissue to show symptoms. That means in an individual, they are asymptomatic. But within their germline, in the cells that are going to produce oocytes or sperm that are going to be, produce their children, they do have that mutation. Okay? So they can pass it on to multiple different children, even though they are asymptomatic themselves. So each of the new children doesn't represent a new mutation. So where you can sometimes see this is with some autosomal dominant diseases where you have asymptomatic parents, but you have multiple affected children. That doesn't make sense with autosomal dominant, right? If they had one child, you could say, well, that's a new mutation. That can happen. If you have two, that doesn't make sense. You're not going to have two children in the same family have the same extremely rare event happen. Okay? So, and one place where that's been studied is type 2 osteogenesis imperfecta. This is the very severe version of osteogenesis imperfecta. Originally, they thought that they thought type 2 was actually autosomal recessive because they would have asymptomatic parents and they would have multiple children with that. But there were cases where they actually had this germline mosaicism, where it actually was an autosomal dominant disease, but they had it in the germline and wasn't present in the parents' somatic tissue. Therefore, they didn't see symptoms, but they had more than one child. So if you have more than one child with an autosomal dominant disease, and they have asymptomatic parents, that's where you suspect germline mosaicism. Next term is penetrance, or in this case, reduced penetrance. So penetrance means when you have a particular genetic disease, how often does somebody who inherits the genotype that should show the disease, how often do they actually show the disease? Up until this point, we've just been assuming if you have a certain genotype, you have the disease, okay? But there are diseases where you don't have 100% penetrance. That means if you looked at the genotype of that individual, they should have a particular condition. And in some cases, they don't always manifest it. One common example that's used to illustrate this concept is retinoblastoma. Okay. Now, about 10% of the cases of retinoblastoma are the inherited version. Okay, there's other versions that are more common. You can have somatic mutations, other things. I'm sure you will talk about that in some other classes. But right now, I'm just talking about the inherited version. And so that accounts for about 10% of the cases, and it's a defect in this RB1 gene. This happens to be a tumor suppressor gene, and this is inherited in an autosomal dominant fashion, right? So this should mean that if you have an affected parent, they can have affected children. If you have an affected child, you should have an affected parent. And here we have a pedigree that could happen with an individual with a case of retinoblastoma. In this case, we actually skipped a generation. You don't see, in normal autosomal dominant pedigrees, you don't see generation skipping. Now, one thing I want to warn you about, one thing I'm going to ask you to do at the end is know the pedigrees. If I give you a pedigree, it's going to be blatant, okay? It's going to be recessive, autosomal dominant, autosomal recessive, X-linked, or mitochondrial. Okay, I'm not going to try to throw a loop for you and throw in one with reduced penetrance. That's impossible for you guys to figure out, okay? So this is a disease we already know is autosomal dominant, and we have a pedigree, so the only way you could test on that is to tell you all that. When I give you a pedigree and ask, you're not going to say, well, and I ask what it is, you're not going to say, well, that could be if this happened and that happened. No. Pick the one that's the most obvious one, the best case scenario, okay? But anyway, here we do have a little bit different pedigree, and we have a parent here where, you could clearly see the gene mutation should have been passed down through that parent. They have the gene, but they didn't show any symptoms. What's going on there? Why did we see reduced penetrance? Well, as it turns out with retinoblastoma, to get the retinoblastoma, which is this eye tumor, okay, you inherit one mutated copy, but what has to happen is your normal copy also has to be inactivated, okay? So that's where autosomal dominant and recessive get a little bit weird as well. It's inherited as a dominant condition, but ultimately the second gene also needs to be knocked out to see the symptoms. In 90% of the cases, you do see symptoms. And why is that? Well, you've got millions, or at least 1 million retinal cells, and each one of those is going to divide. Chances are, if you have that many chances, that you are going to knock out the retinoblastoma gene, the normal copy, in one or a few cells and end up with a retinoblastoma. But if you're extremely lucky, you could have a scenario where you never, in those cell divisions, you never get a knockout. So you can have people who inherited what should be the retinoblastoma condition who don't show the symptoms. Does that make sense to you? Hopefully you get that, and hopefully you can go through that and understand that, because you're going to see this more than you probably want to in cancer. Okay, a lot of cancer disease-causing mutations, you see the same thing where you need 2 hits in order to get the condition to manifest, and so the genetics becomes a little bit complicated because of that. Okay, some other genetic phenomena that could complicate things. You also have some diseases where you have a delayed age of onset. I've also seen recently where I saw that somebody called it age-dependent penetrance. I think delayed age of onset is more common, but age-dependent penetrance is something I've seen that as well. These are disorders so most genetic diseases, the symptoms you see early in childhood. There are a few genetic diseases, single gene disorders I'm talking about right now. With multifactorial, very often they're later in life. But with the single gene disorders, most of the time you see it they manifest very early, but there's a few where the symptoms you don't see until later in life, and that's called delayed age of onset. A couple of examples here, both Huntington disease and myotonic dystrophy, those were both examples of trinucleotide repeat expansions. Also, something else we're going to visit in a second for another reason. In both of those conditions, when you first see this condition in a pedigree, very typically the symptoms aren't until well into life. I said 30s or 40s. I think both with Huntington and myotonic dystrophy, The very first person in a pedigree to show it may even be later than that, could even be in the 50s. What's the consequence of that? Well, unfortunately, in these cases, these are both autosomal dominant. They may have already had children before they even realized they had the disease. In some cases, they may have already had grandchildren before they realized they had the disease. And you'll see that sometimes with Huntington disease. People will have grandchildren before they ever realize they had Huntington, and then both their children and grandchildren now could possibly be affected. And unfortunately, there's no cure for Huntington and really no treatment for Huntington. It's a devastating disease. Another genetic phenomenon, locus heterogeneity. This is when the same disease phenotype can be caused by mutations in different loci. So different genes, in many cases on different chromosomes. So they're located in different physical regions. So it's important to recognize that conditions are very often named clinically. For example, Ehlers-Danlos. They're named clinically based on the symptoms. You have a certain symptomology you follow. They meet a certain number of criteria. They have that disease. So it's not necessarily named on the molecular defect. Now, sometimes there is a very specific molecular defect, but you do have diseases. Ehlers-Danlos is one. There's a whole bunch of different, there's a spectrum of symptoms with Ehlers-Danlos. There's certain things that are common. We've talked about those. But Ehlers-Danlos, the clinical symptoms that you see can be caused by mutations in different genes, a number of different genes. Ehlers-Danlos can also be autosomal recessive. It could be autosomal dominant, and it could be X-linked recessive. And we haven't talked about X-linked yet, but we'll talk about those tomorrow. So how the heck does that, how can that possibly happen?
Yeah, I had a quick question. I know this may be a stretch based on that definition, but could an alpha thalassemia be considered locus heterogeneity?
No, because we're still always talking about that alpha gene locus. I guess, you know, there's two genes there, so, but generally speaking, no. We're just gonna, that wouldn't be locus heterogeneity. It's basically a single locus with two genes in that case. So we're really talking about different, we're talking about diseases where you have a mutation in a completely different gene causing something that's clinically very similar. So how can Ehlers-Danlos, let's just think about autosomal recessive and autosomal dominant, which are things we have seen. Well, you could have mutations, there's mutations in certain collagen genes, that's a structural defect. That would be, a structural defect would be dominant, right? There are certain mutations in collagen genes which you'll see symptoms of Ehlers-Danlos. Whereas you could have a mutation in a gene that is an enzyme that processes collagen, and that would be autosomal recessive. That means if you have 50% of the enzyme, it will still process the collagen normally, maybe not quite as fast, but it can still do it all. So the collagen is normal. So you'd have to have two mutated copies, so that's where it'd be autosomal recessive. And if the gene happens to be located on an X chromosome, you can also get X-linked versions of Ehlers-Danlos as well. Okay? So that is something you can see. Another thing that could complicate pedigrees is a new mutation. Every pedigree starts somewhere with a new mutation, right? And you have to realize that. Now, you can't successfully defend an incorrect answer on an exam while you defended a pedigree saying, well, every single affected individual in there could have been a new mutation. It's a one in an uncountable possible chance. And in the history of infinity, maybe that's possible to happen, okay? So I don't want you to try to use that. So when you see a pedigree, there's always only going to be one new mutation in the pedigree, okay? There's not going to be multiple new mutations in there. But they all have to start from somewhere. And so sometimes that complicates when you only have a partial pedigree to deal with. But if you have cases where the mortality of a disease is very high, or the mutation results in low or absent fertility, Many of the cases, or perhaps all of the cases, have to be due to a new mutation, right? If the person who inherits something that's autosomal dominant and they can't survive to pass it on, well, it's going to have to always be a new mutation, right? If you look at like type 2 osteogenesis imperfecta, that always had to be due to a new mutation because they're not going to survive to pass it on. Now, it could be germline mosaicism. It could have been a new mutation in the germline of the parent, or it could have been a mutation in the individual who had the condition. But I think that makes sense, right? So the more severe the disease, and in particular, you see this with autosomal dominant diseases, where having just a single copy, you manifest the symptoms of the disease. Okay, the recessive genes can actually remain hidden, right? Those can remain hidden because you can always have carriers. An example, 7 of 8 cases of achondroplasia are due to new mutations. People who have achondroplasia certainly can have children, but about 7 out of 8 are due to new mutations. And it does reduce the ability to have children. They can have children, but they're not as fertile as somebody who doesn't have that mutation. The next concept is anticipation. Okay, this isn't what you feel every day before biochemistry class. I'm talking about anticipation in genetics. Okay, so anticipation. This refers to, and this one's my favorite, I guess, because this one's really weird. But you can explain it at the molecular level. So this is diseases where the most recent generations, so if you're looking at a pedigree and you have grandparents, parents, and children, the most recent generation would be the last kids to be born. They show an earlier age of onset and or more severe symptoms. So let's say you had 3 generations of a disease. The grandchildren would be much more severely affected and or show an earlier age of onset of the symptoms than their grandparents. Okay? That's weird. Okay, we're talking about a mutation here. It should be the same, right? It should always just be the same. So how the heck can that possibly happen? Where you actually see this is in our trinucleotide repeat expansion. So that might be a little clue as to what's going on. You do see it with Fragile X syndrome, but with Fragile X syndrome, that means later generations of people with Fragile X syndrome are more severely affected. But Fragile X syndrome typically presents in childhood anyway, so the places where it's most evident, where it's really blatant, are in the cases of myotonic dystrophy and Huntington disease. Why is that? And I'm giving you Huntington or myotonic dystrophy as an example. What's happening is in later generations, that repeat expansion is actually getting bigger. So the severity of the symptoms and the age of onset is directly correlated with the amount of that repeat expansion. Okay, so in somebody with myotonic dystrophy, if you have somebody who's normal, they have 5 to 37 repeats. Remember, that was in the 3' untranslated region of the gene. You can have somebody with mild disease where you have a very late onset of symptoms. And once again, they probably have already had children at this point. Older than 40, they may have already had grandchildren. But they have milder symptoms and a late age of onset. They might have 50 to 100 repeats. And you certainly don't have to try to memorize those numbers. This is just illustrating a principle. Okay? Whereas, in later generations, if this is being passed down, they may eventually have people showing up in the pedigree that have a severe disease. Eventually, with myotonic dystrophy, if it gets passed down long enough, I told you this was an adult onset form of muscular dystrophy. You can have children showing symptoms of myotonic dystrophy if that repeat gets big enough. So that's a good example. The age of onset and the severity of the symptoms is getting much more severe in subsequent generations. So that's anticipation. Now we have a couple things we're going to talk about that contribute to genetic variation. First thing I'm going to mention is mutation rates. For the most part, we're going to assume mutation rates are all the same. The chances of having mutations are all the same. So unless you, live close to a nuclear reactor or something like that, where you have something that's going to constantly expose you to something that causes mutations, okay, or you work in a lab like I do sometimes, for the most part, the mutation rates amongst human populations are stable. Okay, people who lived near Chernobyl had a much higher incidence. Maybe you guys aren't familiar with Chernobyl. I guess I might be dating myself here, but where they had a nuclear explosion, and I actually had a friend who was near there when it happened, and actually died from. She was in graduate school with me. Died of lung cancer and brain cancer in her 30s, which is something you wouldn't typically see, and that was because of that. But anyway, that's as an aside. So mutation rates are generally considered to be the same amongst populations. However, we do have natural selection. So natural selection is going to influence gene frequencies. Okay, so you expect that genes that promote survival and or fertility, okay, we'll refer to that as genetic fitness, are going to be more prevalent in a population. They're going to be selected for. And the genes that cause disease, because they reduce the fitness, or in some cases they eliminate the genetic fitness of an individual, they're going to be selected against because you have the reduced fitness. Okay? Dominant disease genes, remember dominant disease genes, we only need a single copy. They're exposed to selection right away. Recessive genes can remain hidden in a population, and if you have carriers who are otherwise normal, then they're not necessarily going to be selected against. Okay? Until you have an affected person, they're not getting selected against. Ultimately, if the affected person has a disease that affects their fitness, if you look in long-term, scale of years, ultimately that will reduce the amount you see that gene in an autosomal recessive. But in dominant, it happens right away. And that's why dominant disease genes are much less frequently seen in the population than recessive disease genes. Even though in many cases the incidence of disease looks about the same, we did the calculations and you saw those autosomal recessive disease genes are present with almost alarming frequency, okay? Because they're not always being selected against. However, even with natural selection, you do have some genes that are at a higher rate than what you would expect. A very good example is sickle cell anemia. Sickle cell anemia is a very severe disease, absolutely affects the fitness of an individual. It's possible for them to have children, but it's a very severe disease, and it's absolutely going to affect their ability to have children. You'll see sickle cell anemia in some parts of Africa in about 1 in 50 births. So I'll use my Hardy-Weinberg. That's close to 49, right? So 1 over 49, we'll take the square root, is about 1 over 7. Multiply that by 2. 2 over 7 are about 1 in 3.5. That's just a quick rough estimate. About 1 in 3.5 people would be carriers in that instance. That's a very, very, very high rate. Okay? And anytime you see a high rate of a mutation, you should be thinking about what I'm going to talk about right now. And that's the heterozygote advantage. So this is a case where the carriers for an autosomal recessive disease have some kind of advantage over the people who have 2 normal copies. And in Africa, malaria is something that causes a very high incidence of disease, okay? Deadly disease, very severe selection pressure with malaria, right? And so what happens to happen in individuals who are heterozygotes for sickle cell, so they have 1 copy of the mutated gene, otherwise they're normal, except under conditions which I'm sure you've talked a little bit about, so they can manifest symptoms a little bit. But one of the things you'll see is, now they don't not get malaria, but when they get malaria, it's much less severe than somebody who has 2 normal copies of the beta globin gene. So they survive better, so they actually have an advantage. So the heterozygotes have an advantage, and that allows that sickle cell mutation to persist at a relatively high level in those populations. And if the malaria pressure was not there, then what you would expect is that over time, because of the reduced fitness of the people who get 2 copies, the gene would never necessarily go away, but over time it would start to get diluted out, and you'd see the incidence of sickle cell anemia being much less frequent. And actually, you're seeing that in American blacks now. Okay, the sickle cell over time, sickle cell anemia is becoming much less common. Now, there's other things that are contributing to that as well, so that's not the only case where you see that. There's other thalassemias also offer that same type of protection. That's why the thalassemia mutations are so common. I didn't write it here, but glucose-6-phosphate dehydrogenase deficiency, they're also protected against malaria. And it's thought that cystic fibrosis, this was one, we did the calculations, right? You had a carrier rate of about 1 in 25, an incidence of about 1 in 2,500 in Caucasian populations. That's very, very high for a genetic disease which is essentially lethal. Okay, has a very severe reduced fitness in those individuals. Okay, so that's one. And when you see something like that, you have a severe disease but a high incidence, could be a heterozygote advantage. So it's been theorized that heterozygotes for cystic fibrosis, so normal carriers, may be protected against typhoid or cholera. These were things that were much more prevalent many years ago, and so may have been selected. And so now don't offer as much advantage, so cystic fibrosis would be becoming more and more rare, but it's thought that. Now that hasn't been proven yet to my knowledge, and there's also some other hypotheses as well. But okay, the next thing that can contribute to genetic variation is genetic drift. We also call this the founder effect. I actually like the founder effect better because I think it's easier. What it does actually sticks better in my mind when I hear founder effect. But what happens is basically you're starting with a relatively small population that goes on to populate an area. Okay, you could think of it like the easiest way is probably think of it as an island, and you start with 20 people, and eventually they populate the whole island. But you also have populations that, for whatever reason, either geographically or culturally, remain together and don't outbreed, for lack of a better word. And in those populations, certain genes are going to be prevalent at a much higher incidence than you would see in the population at large. Okay? So, and in some cases, these could be rare disease genes. So it could be one individual or a couple individuals in a small population that started an area, had a particular disease gene, and then later on, a significant amount of that population ends up with that rare disease gene. This is sort of related to consanguinity, which we're going to talk about shortly, but it's a little bit different because in these cases, by any pedigree analysis, you couldn't see a relation in these individuals. A good real-world example, and there's a bunch of them out there, but a good real-world example is maple syrup urine disease. This is something you guys have already seen. The incidence of that in the United States is 1 in 180,000. Okay, so that's very, very rare. So you're probably like, why did we have to learn that then? Well, it might be on your board exams. Unfortunately, on your board exams, the rarity doesn't always correlate with whether or not they're going to test you on it. There is other reasons why they make you learn that. If you're interested, you can come and talk to me about it. But in the old order Amish and Mennonite populations in Lancaster County in Pennsylvania, this is an example where you see the founder effect. The incidence of maple syrup urine disease is about 1 in 176 live births, very, very high. There's a number of other genetic diseases in that particular population that are very rare in the rest of the world, but happen to be a high incidence in that particular population. And that's just one population I've chosen. There's others as well. Okay. Now, gene flow is actually the opposite scenario, where you actually have essentially outbreeding, where you have populations that are intermingling, okay, and that would result in gene flow, okay. So a good example of that is United States, right? We have a very mixed population here, and more frequently we're seeing people of different backgrounds coming together and having children, and that's an example of gene flow. From a genetic perspective, that's actually a very good thing, okay? Okay, so next thing we're going to talk about is consanguinity and its health consequences. So we showed you earlier an autosomal recessive pedigree. I told you when we looked at that, you saw a consanguineous mating shown, and I told you when you see that, be thinking autosomal recessive. And why is that? Okay, so when we take an average individual, the number of recessive deleterious genes, so bad genes that an average individual has, okay, that would result in a genetic disease if they had 2 copies of that gene, are about 5 to 8. So all of us, in all likelihood, have some genes in there that if you had 2 copies of it, it would cause a genetic disease. In some cases, the genetic disease could be lethal, and that would be called lethal equivalence. So it's estimated somewhere, an individual contains somewhere between 1 and 5, and you don't have to memorize those numbers. This is just for illustrative purposes. 1 in 5 or 1 to 5 genes would be lethal if you had 2 copies of that mutant gene. Okay? Kind of scary to think about that, you know, in all likelihood, in some pathway in your body, you've only got 1 functional gene there. And in all likelihood, you have multiple cases of that, okay? And in all likelihood, you're going to inherit those from your parents, okay? And when I say most or all, you could have a new mutation. You could be the first person. That's why I say most. But unless it's a new mutation, you got them from your parents, and that means siblings, on average, are going to share about half of those mutations. And actually, parents, on average, would share about half of those mutations. That means direct relatives are far more likely to share those mutations than the rest of the population. We're talking about rare mutations. Okay? If you look at the population as a whole, it's very rare. But you're going to have characteristic mutations that are going to be in your particular family. What that ends up meaning is incestuous or consanguineous matings are far more likely to produce a genetic disease, an autosomal recessive genetic disease, than random mating. In United States, you don't see this a lot. In some parts of the world, consanguineous matings are still normal, are still part of the culture. And it used to be very normal, okay? Even, you know, amongst the royal families and all this. So there, in many years ago, populations tend to be more isolated as well, okay? So I guess in those situations, your cousin starts to look more and more attractive, right? So, and at that time, people didn't know about genetics. The thing is, ultimately, you know, I make some jokes, and we're going to talk about a scenario here, but ultimately, at some point, if you could trace your pedigree back far enough, there would be some inbreeding, okay? There would be some consanguineous matings with every one of us, okay? So we can make some jokes and laugh, but we're all ultimately, at some point, a product of that. Now, so I used to do a whole lecture on this with my students at KaiCom because they're from Kentucky. I cut this down a little bit. I didn't mean that in a bad way, but it was more interesting to them because they were from Kentucky. There are books that mention the Appalachian region as still being a region where you have an isolated population where consanguineous matings can still happen. And believe me, they result in some weird things. But one legendary example was the Kentucky Blue people. Have you heard of the Kentucky Blue people? This is real. This is not something I'm making up. This is a real genetic disease. This is not a lethal genetic disease, so it's kind of an interesting thing. But the disease is methemoglobinemia. Have you talked about methemoglobinemia at all? Okay, good. So you know what methemoglobinemia is. Basically, the iron in hemoglobin gets oxidized from Fe2+ to Fe3+. Okay? When it does that, it can't bind oxygen. If you get enough of that in your blood, okay, it's going to give the blood what appears to be a blue hue through your skin. It's actually brown if you see it in the red blood cells themselves. So, but your skin will start to, if the methemoglobin levels get high enough, your skin will start to appear blue. Also called chocolate cyanosis. Why is that? Well, one thing you can use, so many things can cause you to turn blue, right? I want you to understand that. Methemoglobinemia is one of a small percentage of the possibilities. So if you don't breathe, you'll turn blue, right? But you can differentiate methemoglobinemia from other things that could cause you to turn blue, because in these individuals, if you take a blood sample, their blood actually looks like chocolate. So exposure to the air, you know, if you look at your veins, they also appear blue, right? And that's basically what's happening all over in people with methemoglobinemia. But if you cut it open, it gets exposed to oxygen, immediately turns red, right? With methemoglobinemia, that doesn't happen. They still retain that blue color because they can't, or actually it's a brown color once you see it, once you release the blood. But that's because it can't bind oxygen, okay? And that gives it the color. Now, you can have acquired methemoglobinemia, or you can have the genetic disease. The genetic disease is very, very rare, okay? It's much more common to see acquired versions where oxidative stress can cause methemoglobinemia. Acquired methemoglobinemia is particularly common in infants, okay? And that's because this gene that's going to be mutated in the Kentucky Blue people, which is the NADH methemoglobin reductase, we'll talk about in the next slide, it hasn't reached adult levels yet, so they're much more prone. And you need that enzyme to convert the iron back to the normal version so it can bind oxygen again, okay? So in infants, they don't have enough of that enzyme yet, so they're much more prone to methemoglobinemia. And so nitrates in water, you'll always see that warning. That's why. In babies, you have to be really careful of that. So as you're going through, by the way, as you're going through this PowerPoint, I'm going to get into a little bit of fun stuff after we talk about the methemoglobinemia. The methemoglobinemia, I want you to understand the disease, the acquired versus congenital, what's going on there. I want you to know that. The stuff we talk about, the Kentucky Blue people, is just going to be, I will tell you a little bit about the story. So you can have a genetic disease where you have a deficiency of NADH methemoglobin reductase. That's what happened in the Kentucky Blue people. Also, sometimes you see this diaphorase 1, but I like this name because it tells you exactly what it does, and it's more common to see that name used. NADH methemoglobin reductase. It's actually a very rare genetic disease. You don't see this very often, okay? There are some other genetic diseases where that affect red blood cells that occasionally can cause the presence of methemoglobin and could result in enough methemoglobin where you could occasionally see the symptoms. And these are some things we've seen before. I don't expect you to try to learn those. I want you to know that NADH methemoglobin reductase can cause a genetic version of methemoglobinemia. And I want you to know what methemoglobinemia is. So I always use this as an illustration of consanguinity. We had the Kentucky Blue people, and people had heard about this story, but it's actually true. And what happened is you had many years ago, I think it was back in the 1700s, you happened to have somebody who happened to be a blue person who had this NADH methemoglobin reductase gene, or 2 copies of the mutant version, and a carrier mother, and they had children. About half their children ended up being affected. I think it was 4 and 3. But they were part of a very small population at the beginning, and a very small population that extensively interbred. And so they had all these blue people showing up. And this was there's a link you could click and read the whole story. It's not super long, and it's kind of interesting. I don't have time to explain the whole story, but this is certainly not something I put on an exam and not something for you to try to memorize. But it does show you, and this is a partial pedigree, so if you're trying to look for the 3 and 4 that I mentioned on the last slide, you can't find it. But this is a real pedigree, the best they could put together for the Kentucky Blue people. And the one thing that I want you to notice there is there's a lot of double bars going on there, okay? All kinds of interesting matings going on. And that's why this disease kind of persisted and was popular in this particular population. It still exists, actually, in this population, but there's an easy treatment for it. So if somebody had the condition, you would no longer know, because you could just use methylene blue. Very easy chemical to come. We have this in the lab. Now, the fact that it's blue has nothing to do with the blue color of the condition, but if you give somebody that, it's an alternative way to reduce the iron, and then therefore they can actually become normal. They can make the hemoglobin back to normal. Okay, so it actually works very effectively, very rapidly, no real side effects. So anybody who has this version of methemoglobinemia, you could just take this now and you wouldn't know it. Although students of mine from ChiCom tell me they have run into, so they still run into occasionally a blue person, and they're always super excited to tell me about it. I saw one finally, a Kentucky blue person, so it's real. And just as an aside, and this is also something I'm not going to test you on, but recently this came out that some of the descendants of the McCoy family have this particular autosomal dominant disease. It's got relatively low penetrance, so it can actually remain kind of hidden. It's von Hippel-Lindau syndrome, and one of the things you could see in von Hippel-Lindau syndrome is a pheochromocytoma. And so this is a tumor of the adrenal gland, and people with a pheochromocytoma could sometimes be predisposed to an explosive temper. And they're thinking that maybe way back when, and if you ever saw the story of the Hatfields and McCoys, way back when, apparently Randolph McCoy, one of the original paternal guy in this whole story, had a very short temper, and they're thinking, and that part of what precipitated the whole episode, and they're thinking that maybe he actually, because he was reputed to be very angry a lot, they think maybe he actually had this pheochromocytoma, or this von Hippel-Lindau syndrome. It may have actually caused this whole feud, which is no longer going on. And then and this is what I call the Lucia hypothesis, because I haven't seen this mentioned anywhere else, but if you guys go and watch or read about the history of the Hatfield and McCoy feud, the thing that ended the feud was the hanging of this kid, Ellison Mounts. He was mentally very slow, and he also had very blonde hair. They called him Cotton Top, and they kind of sacrificed him, and that kind of ended the feud. This kid was probably also the result of inbreeding, and the fact that he had blonde hair and was very slow suggests to me he probably had PKU. So there's the Lucia hypothesis. Sorry I ran a little bit long, but sorry about that. Oops.